We have seen thus far examples of electron donating groups by inductive effect, as exemplified by alkyl groups, electron donating groups by resonance, basically groups that have atoms that have a lone pair. The atom with the lone pair must directly be attached or bonded to the benzene ring. We have also seen examples of electron withdrawing groups by inductive effect, such as halogens, for example, or even nitrogen or oxygen, and these atoms are more electronegative than carbon. Therefore, they are entitled to be electron withdrawing groups by inductive effect. Now, to complete the story, there are electron withdrawing groups by resonance. So let's take examples of that type. This is nitrobenzene. Now, in order to understand the electronic effect of the nitro group, we should be able to draw a proper Lewis structure of the nitro group in this nitrobenzene structure. So this is redrawn like this. So this is the proper drawing of nitrobenzene. Nitrogen has a double bond with oxygen in this case, and a single bond with oxygen. Now, if you notice, there is a double bond here. And of course, this is a heteroatom or an electronegative atom. We can break this carbon-carbon double bond to make a double bond here and break this nitrogen-oxygen double bond simultaneously. Let's do that. So we break this carbon-carbon double bond and we make a double bond here, and then we break this nitrogen oxygen double bond. This would only be possible if this atom is actually an electronegative atom. If we do that, then we would get another resonance form. Now, this carbon has lost its electron share here, so therefore it must carry a positive charge. But if it carries a positive charge, it's therefore evident that the electron density in this benzene ring is significantly lowered. Therefore, its nucleophilicity is also significantly lowered, and therefore the reactivity is much less now than in unsubstituted benzene. We can continue with the delocalization of the charge in this case by breaking this carbon-carbon double bond and making a double bond here in order to make that carbon, which is positively charged, neutral. If we do that, we would get another resonance form. But now this carbon must carry a positive charge. We can continue with the charge delocalization by breaking that carbon-carbon double bond and making a double bond here in order to make that carbon, which is positively charged, neutral. And if we do that, we get an additional form. And in this form, it's actually this carbon that's now positively charged. So in all of these cases, the electron density in the benzene ring is significantly reduced, and therefore the nucleophilicity of this substituted benzene is also significantly reduced. And as a result, the nucleophilicity of nitrobenzene is much less than that in unsubstituted benzene as a result of this resonance withdrawal of electrons. So we can therefore describe the NO2 as an electron withdrawing group by resonance, or there is resonance withdrawal if there is resonance withdrawal, therefore the electron density is lowered, and therefore the nucleophilicity is also lowered, and therefore nitrobenzene, or any benzene actually with an electron withdrawing group by resonance, is much less reactive than benzene itself in electrophilic aromatic substitution reactions. We have just seen that the nitro group behaves as an electron withdrawing group by resonance. So this is an electron withdrawing group by resonance. It withdraws electrons from the benzene ring by resonance. That's because it has a multiple bond or a double bond specifically between nitrogen and oxygen. We'll take other examples in order to further illustrate that requirement. In addition to the electron withdrawal ability by resonance of the nitro group, nitrogen is also more electronegative than carbon. So it pulls electrons more in this nitrogen-carbon bond, leaving carbon with a positive partial charge and nitrogen with a negative partial charge. But this inductive withdrawal actually supports, if you like, or coincides with the resonance withdrawal. The two effects, the resonance withdrawal and the inductive withdrawal, therefore reinforce each other. So therefore, the nitro group is an electron withdrawing group by resonance. It's also an electron withdrawing group by inductive effect. This benzene is also described as deactive, if you like. Therefore, the nitro group is also described as deactivating. So it's a deactivating group because now the benzene ring is deactivated. It's much less reactive than unsubstituted benzene itself in electrophilic aromatic substitution reactions.